Yeah, hi everyone. Welcome to day 2 of the Graduate Student Research Conference hosted by the NISS Graduate Student Network. So because of a tight schedule, I'm going to jump up onto the session 2, which is the new developments in risk analysis, bioinformatics, and biomedical application. So let's welcome our first speaker from the University of Connecticut, Surya Ada. Sorry if I pronounce your name wrong. So here I will use a Zoom timer here so you can see your time from your side. So please remember that every speaker only have 15 minutes presentation and then 1 minute of Q&A section. Yeah, so yeah, you can go ahead and share your screen and start.
Thank you so much. Good afternoon once again. Today I'll be talking about Brownian motion governed by telegraph force process with some of its applications to financial time series. If we can go to the next slide. So as an outline, we'll go through the introduction, what motivated to work on this, and then we'll probably formulate mathematically what this BMT process is. And since the aim is to estimate parameters, we'll talk about the transitional densities and the likelihood, and based on which we basically arrive at estimates. And we will show through a simulation study about the parameter inference, and we'll also go through some of its applications. I'm trying to start my video. I hope it'll switch on in some time, but I'm not sure if it doesn't quickly enough start up. So the motivation for this work is that, we know that Brownian motion itself has been used to model stocks, be it in Black-Scholes model or many other different models. So, however, we think that it has a slightly simple characterization with constant volatility, and therefore it might not explain some of the properties that stock prices might have. And there are many other approaches that are built to address these limitations. Let it be stochastic volatility models or Arma-Gauch model or regime switching model that actually at least explain a few more characteristics of the stock price better than what Brownian motion does. So with this in mind, if we can move on to the next slide. With this in mind, we are talking about a two-state continuous Markov switching process, which has two different Brownian motions that have different drifts. If one has positive drift, the other has a negative drift. And we assume that switches happen according to an on-off process that basically moves in 0 and then to 1 and then to 0 and then to 1. And increments within each state will basically follow this Brownian motion. And therefore, the increments that are observed, in essence, follow a hidden Markov process. So we are going to refer to this as a Brownian motion governed by telegraph force process, or simply called as BMT process. We are going to propose the likelihood estimation for these parameters that are involved in this process. So the aim, in essence, is to find the transitional probabilities and then derive the numerical likelihood of it and show you the parametric inference that we observed in simulations, and also show some application-based benchmarking. So moving on to the next slide. So there are a lot of previous studies that have happened, at least with telegraph force process, which is the on-off process, and also sometimes with the telegraph process, which is basically adding a linear movement on this on-off process. This has been widely used now in literature. There has been mean variance hedging of stock options, or this process, the geometric telegraph process, is also used for pricing because it's a process with bounded variation. And in another paper, jump telegraph process is seen to have shown volatility smile as a characteristic of this pricing. So moving on. Oh. So,
Oh.
Yeah. So moving on from the telegraph process, as we recollect, remember that the idea is for the estimation for us. So yeah, the next slide. The idea is for estimation, and estimation has its own challenges for processes such as this. And just to give you an idea, for a discretely observed telegraph process also, there are some works that include pseudo maximum likelihood or moment-based estimators or least square types of estimators. However, there aren't many likelihood estimations done for processes such as this. So we think that we can still achieve likelihood estimation, and that is basically the work that we've done in this paper. And so since states are not observable, we kind of use some of the hidden Markov model frameworks. In particular, we'll use the normalized version of forward algorithm to basically efficiently compute the log likelihood for the parameters of this process. If you, yeah, can go to the next slide, please. So the key takeaways are from the previous studies are that for likelihood calculation, we basically will require some of the transitional probabilities that BMT process will have, along with the, given the states of the telegrapher's process. And for these transitional probabilities, again, we are going to rely on a few properties that the Brownian motion itself has, which is like the fact that it has independent increments and that it is infinitely divisible, and also some of the results from occupation times of telegrapher's process. The results of occupation times for telegrapher's process these are seen in various papers already, and those are the ones that we've built this work on. And directly speaking, this work basically extends some of the similar work that is done on some driftless Brownian motions that are applied to animal movement model by Shawan, who's worked with my advisors. So moving on. So now we could formulate the BMT process. And in order to mathematically formulate the BMT process, now let's talk about the telegrapher's process or telegrapher's signal process, ST, which is nothing but a continuous time Markov chain that alternates between two states 0 and 1. Remember that this is in continuous time, and therefore the rate matrix that this particularly possesses is basically given by Q or math Q, that is minus lambda naught, lambda 1, minus lambda 1, that in essence indicates that in each particular state, for example, in state 0, the holding time will be exponentially distributed with mean 1 over lambda naught, and before it moves to the state 1, and in state 1, it again is going to have a holding time that is exponentially distributed with mean 1 over lambda 1. So the time it stays in state 0s and state 1s are going to be random and with exponential distribution. The stationary distribution that basically that we have for this particular Markov chain is what we'll use as the initial distribution for S0 that we'll use in the computations of the likelihood later on. So we can see that the stationary distribution is what we get by pi q is equal to 0, and that is given by pi, which is given in this equation over here. So moving on to the next slide. So in order to continue discussing BMT process XT, we need to first, again, add WT, which is a standard Brownian motion to it. So assuming that WT and the previous ST are independent, we say that the BMT process XT is going to have the stochastic differential equation, that is dx of t is going to be either mu naught dt, that is the trend with mu naught drift, plus sigma naught dwt whenever ST is 0. And it's going to be mu1 dt plus sigma 1 dwt when ST is equal to 1, which basically implies that it has its own Brownian motion depending on which state it possesses. So whenever it is in state 0 for a while, it will behave like a Brownian motion with mu naught and sigma naught as its parameters. And when it's in state 1, it behaves like a Brownian motion with parameters mu1 and sigma 1. And here we assume that mu1 is going to be negative and mu naught, sigma 1 are all going to be positive. So that is the restriction that we place on this particular process. So moving on. So we can see an illustration of a Brownian motion driven by telegraph process with a certain parameter that we used here. We can see that this is how one particular simulation might have looked. We have kind of considered that in the negative drift, we might have higher volatility compared to when there is a positive drift. which is what sometimes we expect in stock prices in general. So that is this is just one simulation that we observe here. So moving on. So the goals and challenges. So the goal is to obviously compute the efficient MLE procedure for theta. So here theta basically has all these 6 different parameters, lambda 1, lambda naught, which are the exponential time parameters, and then mu 1, mu naught, sigma 1, sigma naught, which are corresponding to the Brownian motions that are state specific. So we assume that we observe the process from 0 to time tn as 0, xt1, xt2, xt3, xtn. And these could be, these time points t1, t2, tn can all be irregularly spaced. We assume that we start at 0. If we don't start at 0, we kind of move it to 0. And the challenge here is that xt itself is not Markov. It does not have Markovian property. However, the solution that we use is the fact that we observe xt comma st, the 2-dimensional state space process. That happens to be Markov along with stationary increments. And therefore, we use that along with some of the techniques that we, tools that we have from hidden Markov models. The idea is to come up with the transitional probability initially, that is probability that from xs to xt plus s, the increment is around x. So we try to find the density for that. So probability of xt plus s belonging to y plus dx, st plus s is equal to j, given xs is equal to y, comma ss is equal to I. So that we start at initial state I to moving to terminal state j by making an increment of dx of x. That is equivalent to probability of xt taking staying in that interval of dx, st being j given s naught is equal to I, because it has stationary increments, because the 2-dimensional process has stationary increments. So moving on. So now we'll talk about the transitional densities. In the transitional densities, we'll have to talk about occupational time. So of course, for likelihood computation, we'll need these transitional densities. But before that, we define the occupation time that we have in state 0 of state 1. So the occupation time in 0 state ut is defined as nothing but the integral of indicator ss is equal to 0 ds, which is nothing but the total amount of time that you've spent in the interval 0 to t in state 0. And similarly, dt can be defined as t minus ut, because if ut is known, then dt is kind of obviously known. So we cannot think of this as the holding times, because sometimes if your interval is large enough, you might have spent a certain time in state 0, move to state 1, and then again move to state 0, and then again to move state 1 within this interval. And therefore, occupation time can be thought of as the sum of all the holding times in state 0s of state 1 correspondingly. So we'll be using the notation pi of dot, because most of our transitional densities, if you have seen, are all conditioned upon the initial state s given s naught is equal to I. So we'll use the notation pi as the probability of something given s naught is I, which is given the initial state is I. Moving on. So now, given that we've defined what occupation time is, we'll figure out the conditional density of occupation time along with the terminal state given the initial state. So given the initial state is 0, the occupation time belonging to du basically is the density, density at u. So ut belonging to du, comma st is equal to j would give us the occupation time in state 0's density, whereas P1J UT is nothing but if you start at state 1, what is the density of dt, which is the probability, the density of occupation time in state 1. So by the way, these have already been derived in a previous paper. These come across as an infinite sum depending on how many number of cycles or subcycles there were in 0 to t, because ut can be u based on many summations being many summations depending on the number of cycles that we have there. So for example, p naught naught ut can be evaluated as lambda 1 summation k is equal to 1 to infinity exponential of minus lambda naught u minus lambda 1 t minus u, lambda naught u to the power k, lambda 1 t minus u to the power k minus 1, divided by k factorial k minus 1 factorial. If you look at it closely, it might look like a summation of a convolution of two Poisson random variables. Moving on.
Hi, Surya. You only have 1 minute and 30 seconds to wrap up. So
okay, can we? Yeah, so then let's quickly move on to the next slides, and I'll probably wrap up quickly enough. So we'll use Bessel functions to kind of simplify this for efficient calculations. And we also realize that there are some point masses that we have at u is equal to t, because sometimes if there is no switch, there is some extra thing. So the densities occupation times we observe as this: P0 naught, P0 1, P1 0, P1 1. We can simplify as this, and then moving on. Given these P functions, we can come across with the H functions in the next slide. We can come across with the H functions, which are the density of increments. You can see that xt given ut is normally distributed. So we use that to come across with phi multiplied by p0 naught or phi multiplied by p0 1, and integrating it to come across to come up with a final transitional density functions. And you can also see the additional e to the power minus lambda naught or e to the power minus lambda 1 term that is coming because of the point mass that we have. So moving on to the next slides. Yeah, so using these, we actually come across with the likelihood. Of course, remember that we don't observe STs, and therefore we can either take sum over all the combinations of S values, or in the next slides, we'll see that we can use the dynamic programming approach, which has normalized forward algorithm. For example, yeah, over here, we can define the forward variables alphas, which are nothing but the likelihoods of theta, given that we observed the first L elements of the increments and the terminal state. So we have recursive formulas that kind of reduce the complexity of the problem from exponential complexity to linear complexity. So if we go to the next slides, we see that we use this particular method to derive our likelihood. And the likelihoods algorithm is given in the next slides. So can we move on to the next slide? Yeah. So the likelihoods algorithm is given over here. And using this, we have implemented this entirely in R. And using this, we have tried a certain simulation approach, and we chose a certain parameter based on fitting this to a Apple stock. Based on that, when we got our results, we can see the results in the next slides. We can see the violin plots, for example, in the next slide, where we observe that the true value, which is the horizontal line, is close, and we have the violin plot around it. And we also see that in our table, we observe that the estimated values are very close to the true values with decent coverage probabilities that we observe. So if we go to the next table, yeah. Sorry about that. Yeah.
Actually, you might want to stop here because we're already out of time. And
yeah.
Are there any questions here? We only have time for one question. Okay. If not, let's move on to the next speaker. Sorry. Yeah, we might have time to come back to your question later. So the last speaker is from the Ohio State University. Yeah, Dalton, you can go ahead and start. So, can you see my timer? So I will set a timer of 15 minutes.
Yes, I can.
Okay, sure, great. You can go ahead and start.
Okay, can everyone see my screen? Full screen mode? Okay, perfect. Hi, everyone. My name is Dalton Hopper, and I am a statistics PhD student at Ohio State. Today, I'll be discussing a new two-stage design that I have proposed, the order-restricted cluster randomized design, abbreviated ORCRD. The ORCRD is a variation of the traditional cluster randomized design. So we will discuss some important information on CRDs first. Then we will dive into the ORCRD. So we'll discuss models, propose an approximate F-test for the treatment effect, discuss simulation results, and calculate optimal sample sizes. And I'll finally just mention some future work that I plan on doing as well. So sometimes the goal of an experiment is to assess intervention effects of a methodology or a policy on a collective body rather than on individual experimental units. So if this is the case, treatment should be randomly allocated to clusters instead of subjects within those clusters. So some examples of common cluster units you might think of are hospitals, schools, neighborhoods, but designs that are characterized by this type of randomization scheme are referred to as cluster randomized designs. So here we illustrate what's going on in a traditional CRD with a treatment and a control group. So at the top, you see there's some population of interest. From the population of interest, we take simple random samples of cluster units, and from each cluster unit, we take a simple random sample of individuals. So the treatment and control are randomly allocated to the cluster units, and the within cluster units are receiving that corresponding treatment or control. CRDs are very advantageous. They're often more practical, first of all, than completely randomized designs. And they've been used to evaluate health treatment programs, vaccination programs, educational intervention programs. The list continues. They also mitigate the effects of contamination, which occurs when subjects in one treatment group influence subjects in another treatment group. CRDs also come with disadvantages though. So first of all, they're not as powerful as completely randomized designs. And planning a CRD is also more complex since there are two sample sizes to consider. So we have the number of cluster units, and we also have the number of within cluster units as well. But hope is not lost. Work has been done to improve the efficiency of CRDs. For example, some researchers have embedded ranked set sampling, abbreviated RSS, into CRDs. One of these researchers being my dissertation advisor, Dr. Omer Ozturk. But RSS at the core is a sampling technique where units are ranked from smallest to largest using some procedure that doesn't require full measurement. However, a limitation of RSS is that it involves discarding experimental units. So we propose the ORCRD, another variation of the traditional CRD that does utilize ranking information. The ORCRD uses order-restricted randomization, abbreviated ORR, at the cluster level, which has never been done before, and either RSS or SRS, so simple random sampling, at the subsampling level. Now, Drs. Ozturk and Steve McEachran, both professors here at Ohio State, introduced ORR. The general frameworks of ORR and RSS are similar. However, ORR involves ranking and fully measuring all experimental units in a set so that no experimental units are wasted. And then using a restricted method of randomization, within set units in an ORR design are assigned to different treatments. So this assignment, along with that positive correlation among within set units from that ranking procedure, ultimately reduces the variance of, for example, treatment contrast estimators. Now, the ORCRD starts as a randomized block design with H1 blocks. Cluster units are entered into the design as follows. So step one, we randomly select a set of, say, H1 cluster units from the first block. We rank these clusters from smallest to largest using pre-experimental information, and we repeat this process until there are, say, N sets of ranked cluster units in that first block. So we'll use the same process for the other blocks as well. And on this next slide, I just want to illustrate one possible cluster level layout of the ORCRD. So this is an example where H1 is equal to 3. So we have 3 blocks, 3 cluster ranking groups, and also 3 treatments. As you can see, the cluster units are organized into a row column structure. So the rows are indexed by 2 variables, block and set. And the columns are indexed by that ranking variable only. So the block and rank indices define H1 squared cells. So this group of M cluster units here is a cell. This group of M cluster units is a cell. You get the idea. So the H1 treatments are randomly allocated to these cells with the following restriction. Each treatment appears only once in each block and once in each cluster rank. So our design does have a Latin square structure, and I've tried to emphasize the structure here. So notice that treatment 1 is red, treatment 2 is blue, and treatment 3 is brown, and each of those colors is appearing only once in each block in column. And then just some other notes about our design. So we include M sets in each block to increase that degrees of freedom for the cluster error. And I'll talk a little bit more about that later. And then clusters in the same set are correlated due to the ranking mechanism. And then from each cluster, subjects can be selected again using either RSS or SRS. Now we propose the following model for the ORCRD with RSS at the subsampling level. So that's the one I'll be focusing on. So mu is the grand mean in this model. Alpha I is the block effect, beta H is the treatment effect, phi k star is the cluster level ranking group effect, and omega v star is the subsampling level ranking group effect. These are fixed effects with the usual sum to zero constraints. D sub Ri is the effect of set R nested within the ith block. So we treat this as a standard normal random variable, and we put the scale parameter tau is what we use outside in the model, or out front in the model. C star sub Rik is the error term for cluster R nested within cell Ik. So this is the kth, what we call judgment order statistic, and I'll explain what that means in a second, with shifted mean 0 and a set of size H1 from a standard normal distribution. So we're actually shifting that mean to that phi k star term in our model. And again, our scale parameter gamma is out front in the model. So the term judgment order statistic, we use that to indicate that these might not be actual order statistics since there are errors in ranking that can occur. And we'll talk about how to model that on the next few slides. But the epsilon term is the individual error term. It's defined similarly to the cluster error term. And we assume mutual independence among the set effect and the error terms. And then one final note on this slide, just about notation. So this H equals B IK term at the top here, that just signifies that our design is incomplete. So that's due to the Latin square structure. So there's not observations for all possible combinations of IK and H. So we assume there exists an auxiliary variable W that can be used to rank clusters. We propose the following model to account for potential ranking errors. So this C star term represents the judgment ranked cluster error with shifted mean 0. So in this model, row 1 is the correlation between the unordered cluster error and the corresponding W value. These two quantities are assumed to be standard normal random variables. U sub Rik is a noise variable that makes it more difficult to obtain an accurate ranking when row 1 is small. And this variable is also standard normal. And then W plus sub Rik is the kth order statistic in a set of size H1 from a standard normal distribution. And phi k is that corresponding expected value of that order statistic. Now we use analogous logic for the subsampling level ranking model. Due to time constraints, I won't go into detail about this one. But under the ranking model for the cluster errors, phi k star is equal to row 1 times phi k. So this gamma phi k star term in our general model that we had, that's outlined in red, now becomes row 1 times gamma times phi k in the revised model. The cluster error in the general model is replaced by our ranking model expression from a few slides ago. These are outlined in blue. And then the same idea goes for the subsampling rank effect and the subsampling error terms. Now, table 2 contains the EMS expressions for the ORCRD under the stage 1 and 2 ranking models. The two expressions in red boxes suggest an approximate F statistic for the treatment effect is the ratio of the mean squared treatment, because remember our treatment was factor B, and our mean squared cluster error. So under the null hypothesis, for example, of no treatment effect, this ratio is equal to 1. So let's now consider an approximate F-test for the treatment effect. We have the null hypothesis that all treatment effects are equal, and the alternative hypothesis that at least two of the treatment effects differ. Now, an approximate F-test rejects the null hypothesis if FB exceeds the corresponding critical value. And we ran a simulation study investigating type 1 error rates for various correlation structures, sample sizes, and ICC values. And ICC is this quantity defined here. All of these were very close to the nominal value of 0.05, which was really exciting to see. Now, to investigate the null distribution of FB further, we performed a simulation study under our revised ORCRD model. So these are the simulation parameters we used. We used a simulation size of 10,000. And on this next slide, we include some of these QQ plots. So we made a ton. This is a very select few, but the first row corresponds to ICC equal to 0.01. The second row corresponds to ICC equal to 0.5. H1 and M are increasing as we move from left to right across the columns. And notice that each panel actually contains two QQ plots. So the black points correspond to the exact F distribution, so completely random rankings. The red points correspond to various ranking qualities using our ranking models. Now the QQ plots here show approximate linearity, and the red and black points in each panel are fairly close together. There is more deviation between the plots when H1 equals 2 and M equals 3, so this leftmost column here, but this is probably due to the smaller denominator degrees of freedom that we have. But regardless, even when row 1 and row 2 are not close to 0, the F distribution approximates the null distribution of FB reasonably well. And we observe similar results for the simulation parameters not presented here also. So we conducted another simulation study to investigate the empirical power of FB. We computed the empirical power under the following alternative hypotheses, where capital delta is defined here and lowercase delta ranges from 0 to 1 in increments of 0.2. So on this slide, we have some power curves of FB when row 2 is equal to 1. The first row corresponds to ICC equals 0.01. The second row corresponds to ICC equal to 0.5. Each panel contains the power curves for various row 1 and H1 values. So I know it's kind of hard to see this. Oh, sorry. I know it's kind of hard to see the legend. I was kind of limited on where I could put it to fit everything in. But notice from this legend, I just want to talk a little bit of detail. So curves with the same color have the same row 1 values, like the black curves, row 1 equals 0, red, row 1 equals 5. Curves with the same line type have the same H1 value. So all of the solid lines have H1 equal to 3. All of the dotted lines have H1 equal to 4. Oh, sorry, I did it again. So let me zoom back out. Okay. So the empirical power is an increasing function of M, H1, and row 1. It's a decreasing function of ICC. Now notice there's not much change in the power curves in the first row, but this clearly is not the case for the second row. So this suggests that for a larger ICC, better ranking quality at the cluster level has more of an impact on the empirical power than when ICC is smaller. Now, to maximize the overall information content of the experiment for a given budget, we must determine the optimal number of units at each stage. So the cost model we use in this optimization problem is at the top of this slide. In this equation, T is the total budget, C1 is the sampling cost for a cluster unit, C2 is the sampling cost for a within cluster unit, and P is the number of sampled within cluster units. The optimal P and M are expressed here. And then finally, just some other results. Oh, yeah.
Could you wrap it up in 1 minute?
Yes. Yeah, I'm almost done. Thank you. Some other results. The ORCRD is at least as efficient as CRDs that currently exist in the literature. General treatment contrast estimators are asymptotically normal. And we've constructed individual and family-wise confidence intervals for treatment contrast. But due to time constraints, I just couldn't go into all the details of this stuff today. And then soon I'm going to apply the ORCRD models to real data. So I'm currently looking at data from the National Center for Education Statistics. I'll also investigate the asymptotic distribution of FB. I expect it to be close to a scaled chi-square distribution, regardless of what the ranking qualities are. And I also plan to estimate and construct confidence intervals for that ICC as well. And that's all I have. So thank you for listening. And here's a list of references.
Thank you, Dalton. Yeah, we have about 2 minutes for questions. Are there any questions for this great presentation? Okay, yeah, if no, we can move on to the next speaker, and then later on, when we have time, we can come back to the Q&A for the previous speaker. Thank you, Dalton.
Thank you.
And then let's welcome the next speaker, who is also from the University of Connecticut. It's Swathi.
Hi there. May I start sharing my screen?
Yeah, sure. Can you see my timer? So I set the timer as 15 minutes. You can go ahead and start.
Okay. Thank you for that. Good afternoon, everyone. My name is Swathi. I'm a fourth-year PhD student at the Department of Statistics at University of Connecticut. And today I'd like to talk about one of my research projects, which is a new formulation of minimum risk fixed width confidence intervals, MRFWCI, for a normal mean. Can we move to the next slide, please? All right, the main aim of this presentation is to develop a minimum risk fixed width confidence interval, JN, for the unknown mean mu of a normal distribution based on a random sample of size n, such that the length of this confidence interval JN is 2 times d, where d is a fixed and known quantity. The coverage probability, that is the probability that mu is included in our confidence interval, exceeds 1 minus alpha, where alpha is fixed. And the risk associated with the terminal strategy of mu, Rn, is minimized. Next slide, please. Thank you. So under the traditional fixed width confidence interval, the FWCI methodologies, one treats the associated confidence interval, confidence coefficient, as the main focus. So we would like to take as many observations in such a way that we are able to achieve the minimum coverage probability of 1 minus alpha. So in these kinds of formulations, you do not encounter the cost of observing each observation at all. So it's almost as if treating that you can take as many observations as you want, as long as you're able to achieve the confidence coefficient that you specified. However, the minimum risk point estimation strategies, one openly balances estimation error by taking into account the cost of sampling as well. So you attach a loss function and a corresponding risk function to your estimation strategy, so that you also so that it balances estimation error with cost of observing that data set as well. So in this presentation, we try to formulate a new method to combine the MRPE and the FWCI methodologies with desired asymptotic second order characteristics under a unified theory to develop the MRFWCI. Next slide. All right, so the general FWCI setup goes like this. We start with X1, X2, Xn, and so on, which represent IID observations from a common normal distribution with mean mu and variance sigma square. Here, both mu and sigma are assumed to be unknown. After recording a fixed number of observations, say n, we can denote the sample mean and sample variance by x bar n and Sn square respectively. Next slide. So having fixed pre-assigned numbers d, which is a positive quantity, and alpha, which lies between 0 to 1, the FWCI, the fixed width confidence interval for the unknown mu, is given by j sub little n, which is x bar n plus or minus d, which you can see clearly has fixed width 2 times d. The confidence coefficient associated with Jn has been calculated in equation 1. And to achieve that this quantity exceeds 1 minus alpha, we can find that n would be the smallest integer, which would exceed z square alpha over 2 sigma square over d square, where z alpha over 2 stands for the upper 100 alpha over 2 percentage point of the standard normal distribution. So this quantity is denoted as n star. So you want n to exceed this quantity, which is n star, to achieve the confidence coefficient you need. The next slide, please. So n star in this equation is called the optimal fixed sample size that is required to construct the FWCI Jn for mu had sigma been known. However, since sigma square is unknown, n star is also unknown. In his 1940 paper, Danzig showed that there does not exist a fixed sample size methodology to solve this problem. So various researchers such as Stein, Anscombe, Chow and Robbins, and Ray developed multiple pioneering multi-stage and purely sequential strategies to address this FWCI problem. Next slide, please. Oh. Can we, you can just click on one of the buttons at the top and it will take you back. So a little further. Yeah, further back. All right. So we start with the development of a new methodology where with the traditional FWCI, we want to associate an appropriate loss and risk function such that it minimizes the risk in such a way that it gives you the same n star from equation 1 that gives you the, in such a way that you can also achieve the confidence coefficient that you set out with. So we may initiate the following idea for a loss function in practice given in equation 2, where the loss consists of two parts, an estimation error and a cost function. The estimation error refers to the non-coverage of mu by our confidence interval. So that probability is given by equation 3. And you can see that this Pn converges to 0 as n goes higher and higher, which is intuitive. Next, can you go to the next slide, please? All right. So for fixed d, alpha, rho, and sigma, we can incorporate this form of the cost function given by equation 4. So combining all of this, we can now present the loss function for any fixed rho, which lies between 0 and 1, 1 inclusive, as what is given in equation 5. Cn comes from equation 4, and the non-coverage probability is what we discussed earlier. Next slide, please. We can also find the risk function by taking the expected value of the loss function, which you can see in equation number 6. Considering this as a continuous function in n, you can see this is a convex function in n. We can differentiate it with respect to n, equate it to 0 to find that value of n, which minimizes the risk. And we can see that the value of n that minimizes the risk is same as n star that we had discussed earlier. So now we can propose a MRFWCI setup finally. Next slide, please. All right. So starting with a pilot sample of size m, which is at least 2, which does not, in the calculation of m does not depend on d. We'll discuss different multi-stage sampling procedures later, where the boundary conditions for stopping, the stopping value of n depends only on sample variances. The event n equals n will depend only on sm square through sn square for all n. So we can use the Basu's theorem to claim that the event that your random variable n will be exactly equal to some quantity will be independent of x bar n for all values of n which are greater than or equal to m. Next slide. All right, so the MRFWCI for the unknown mu based on the recorded observations n and x1, x2, so on until xn is given over here by J capital N, which is x bar n. N represents a random variable, which you decide by adaptively sampling and then choosing n appropriately. The risk function R capital N for the terminal strategy is given at the bottom of the page. We again can get to this equation because we use the fact that indicator n equals n and x bar n are independent. Next slide. So now we start with developing a set of properties for the MRFWCI sampling methodology. So without specifying a specific sampling strategy, we can assume a number of key associated properties as d goes to 0. Property A1, which is called the asymptotic second order efficiency, tells us the expected value of n in terms of n star and some additional constant A1. A2 gives you the limiting distribution of n as d tends to infinity. A3 gives you the tail probability of random variable n, and A4 talks about the uniform integrability of absolute value of h to the power A4. So these characteristics will hold for different, properties will hold for different sampling strategies that I will talk about in just another minute. And the values of A1, A2, A3, and A4 are known. So based on assuming these properties A1 through A4, we can now set up some asymptotic first order and second order properties for the MRFWCI strategies. Next slide, please. So these are the asymptotic first order strategies for the loss function that we discussed earlier and fixed values of alpha, rho, and theta, which is mu and sigma. And AI is defined from the assumptions that we just discussed on the previous slide. We have the following asymptotic properties as d tends to 0. The first property is n over n star converges in probability to 1. Second probability is also called the asymptotic first order efficiency property, which says that expectation of n over c to the power k goes in probability to 1. Third probability gives us the asymptotic consistency property, which states that as d goes to 0, the coverage probability converges in probability to the target 1 minus alpha. And finally, this quantity risk efficiency, which is calculated as the ratio of risk under our sampling strategy divided by the optimal risk for n star. This goes to 1 as d tends to 0. This is the asymptotic risk efficiency property. Next, we have certain asymptotic second order properties for these methodologies. Can we go to the next slide? So you can see for A3, at least for A3 exceeds 5 over 2 and A4 equals to 2 in the properties A1 to A4 that we had discussed earlier. We have the key points that I'd like to highlight are properties 2 and 3, where property 2 gives you a second order expansion of the coverage probability, and property 3 gives you a second order expansion of the risk efficiency. These properties we will later verify by substituting values of A6 and A7 for different methodologies. And you can see A6 and A7 can easily be determined using A1 and A2. Moving on. We can also calculate this quantity called regret, which is calculated as the difference between the risk for our sampling strategy and the risk under the optimal value of n, which is n star, given by this approximation. A7 has been calculated the same way as A7 was on the previous slide for the risk efficiency expansion. Next, I'd like to go over a couple of multi-stage and purely sequential sampling methodologies that are generally implemented. The first example is a purely sequential sampling strategy where we start with a pilot set of observations, say M observations, and then record one additional observation at a time using this following stopping rule. Our final sample size is that sample size which exceeds this quantity z square alpha over 2 Sn square over d square. Once we identify our final sample size, we collect that many observations and derive the MRFWCI given by J capital N. Another sampling strategy that is frequently used is called the accelerated sequential sampling strategy. This is an improvement over the purely sequential. It accelerates the stopping rule by first starting with an integer k and beginning with the same sample observations x1 through xm. And then you try to use a purely sequential methodology to estimate a fraction of your final sample size. So T over here goes the same way as we defined a stopping sample in the purely sequential, except now T tries to mimic the expression of K inverse times N star. So N, which approximates N star, can be calculated as K times T. And that gives us our final sample size and the corresponding MRFWCI JN. Another sampling strategy that is very popular is the 3-stage sampling strategy, where observations are collected in batches in 3 steps. So we start with a sample size of size M, which is a pilot, choose a suitable number kappa, which lies somewhere between 0 and 1, and then calculate T as maximum between M and kappa times this quantity z square alpha over 2 Sm square over d square plus 1. So if T exceeds M, then you consider the remaining M minus T observations from the sample, and now you will have a sample of size T observations. Based on T, we can calculate our final sample size N according to the rule given here. And once we've identified N, we can get the corresponding MRFWCI. So as you can see, with each of these sampling strategies, the way to collect the sample size, to select the sample size changes, but at the end of the day, each sample size that we get to N tries to mimic the value of N star. Next slide. Finally, I talk about the two-stage sampling strategy, one of the quickest sampling strategies there is, but with a small assumption that we know some lower bound for the unknown sigma and denoted by sigma L. So if you know some plausible value of sigma L, we can estimate the sample size M using sigma L, and based on that, we can calculate the final sample size N. So sampling is done in only 2 batches, thus resulting in terminal sample size N and the corresponding MRFWCI. I know I'm out of time. Let me just quickly go through the simulation results and I'll be done. So these are for A1 and A2 for the different sampling strategies that we've just discussed. I've applied this analysis, this MRFWCI for the unknown mean for real data analysis where I've collected observations. Can you go to the next slide, please? Yeah. So I've demonstrated its application by applying it to air quality data set that describes air quality measurements in New York. Variable of interest was wind speed, which we tested was normally distributed using the Chaparral test. And the mean and standard deviation for the full data set are mentioned here, but these were not used when we were calculating the confidence intervals. So if we can go to the next slide. The table on the next page will give us the values of terminal sample size, mu hat n, and jn, which is the confidence interval. We've tried to build a 95% confidence interval for different values of d. The value, you can see what the values of n are. And at the end of the day, our aim is to use jn to estimate unknown mean mu. If we can go a little further, I have also done simulation studies to verify the properties of the different things that we've discussed earlier, the properties discussed in the 2 theorems that we discussed earlier. Those properties are verified if we look at the values in this table. So 10,000 replications for normal with mean mu 25 and sigma square 16. Population for alpha equals 0.05 and rho equals 1 were conducted, and these are the results. You can see n bar approximates n star very closely. P bar is close to the target coverage probability of 95%, and omega bar, which represents risk efficiency, is close to the target value of 1 for all the 4 different sampling strategies that we had discussed. This page gives you the details of simulation results for the purely sequential and accelerated sequential methodology. The next page gives you the performance of the 3-stage and the 2-stage methodologies. Finally, in conclusion, I'd like to say that this particular, can we go to, yeah. So when we are handling the typical FWCI problems, the lack of a loss function creates a false impression that perhaps observations do not cost at all, or one's available budget is unlimited. In the MRFWCI formulation, an FWCI has been casted in the light of an MRPE problem by balancing estimation error with cost of sampling. So these results have been discussed in our 2022 paper. This is a joint work with my advisor, Professor Nitish Mukhopadhyay at the University of Connecticut. So thank you for your time. I really appreciate it. And if you have any questions, I'd be happy to answer them.
Are there any questions from the audience? Yeah, if no, we can move on to the last speaker from Florida State University. Pengfei, you can go ahead and share your screen so we can have all the Q&A in the end. So I will start my timer. Can you see my timer?
Yes, I can. Can you see my screen?
Yes.
Hello, everyone. My name is Pengfei Lu. I'm a PhD candidate of Florida State. Today, I'm very glad to talk about new work, job replicability analysis of high-throughput experiments with application to special transcriptomic studies. This is my outline. Let's begin with the introduction. Replicability is a cornerstone of scientific research. If one certain problem is focused on by different studies, and these studies may be using different procedures or from different populations, we can claim their findings to be replicable if consistent results can be obtained from the studies. In modern high-throughput experiments, the total number of the problems can be thousands or even millions, So we need to evaluate the candidate problems simultaneously. An example is that we want to test the association between different genes to a certain biological feature, like Alzheimer's disease or heart disease. Among the thousands of genes, maybe only about 50 of them would have a correlation. We need to do a multiple testing or multiple comparison to find them. Imagine we have M hypotheses. Among them, M0 would be null and the other M1 would be non-null. For some method, we can reject some hypotheses and accept the others. This table shows a total number of null or non-null hypotheses that we accept or reject. For example, V here would be the total number of null hypotheses that we reject. We call it false rejections or false discoveries. Similarly, S would be the total number of non-null hypotheses that we reject. We call it false true rejections or true discoveries. We need to know that for all of these numbers, we can only in the last line, total number of acceptance, rejections, and total number of hypotheses can be available to us. Or these other numbers could not be observed because we don't know which hypotheses are null and which are non-null. So we need to get estimations of some of numbers. To evaluate the performance of method, a classic criteria for type 1 error is false discovery rate, or FDR, proposed by Benjamin and Hochberg. It is one of the mostly cited papers in statistics. It has been cited for more than 95,000 times. The FDR is defined as the expected ratio of false rejections among total number of rejections. Here, this symbol denotes the maximum of R and 1 to make sure the denominator is non-zero. And the power is defined as the expected ratio of true rejections among total number of non-nulls. A good method must control the FDR at a given level and has high power. To control the FDR, BH is a classic method. With the input MP values from this hypothesis, and we want to control the FDR at some given level alpha. We can first order the p-values from smallest to the largest. Then we find the largest k, where the k-ordered p-value is upper bounded by alpha k over m. With this k, we can reject all the null hypotheses corresponding to the first k ordered p-values. BH could control the FDR at level pi 0 times alpha if the non-significant p-values are independent and follow a standard uniform distribution. Here, pi 0 is a null proportion. When we have two studies and we want to test replicability with BH procedure, a naive way is to apply BH to each of the studies and find discoveries. Then we can claim a gene is replicable if it is significant in both studies. However, this naive method could not control the FDR. Another approach is maximum P. It first gets a maximum P values from two studies for each gene and then directly apply BH procedure to the maximum P values. This procedure can control the FDR, but we found that the FDR is too conservative and consequently the power is low. To obtain higher power, we propose an joint super uniform maximum P value procedure or JUMP by assuming the hidden states of the composite null and giving an approximation of the CDF of maximum P under the null. Next, let's look at the details of JUMP. The input would be n pairs of p-values from two studies, and the null hypothesis for the S gene is that it is not replicable across the two studies. For the observed p-values, we assume they follow a mixed distribution. Denote theta to be the indicator function of the significance. It equals 1 if the p-values are significant. Otherwise, theta would be equal to 0. So look at these two equations. It shows that all the significant p-values would follow some unknown decreasing density functions f1 and f2, and the non-significant p-values would follow some null distribution f0. If we denote tau to be the vector of theta 1 and theta 2 as the joint hidden states across the two studies, it has 4 possible values as shown in this table. With corresponding probabilities, we denote them as Xi. We have some properties of the hidden state probabilities. For example, the summation of all these 4 probabilities would be equal to 1. If we denote pi 0, 1 to be the probability that theta 1 equals 0, it should be the first row in this table. Then pi 0, 1 would be the summation of Xi 0, 0 and Xi 0, 1. Similarly, pi 0, 2, the probability that theta 2 equals 0, is the first column in this table. So it equals to Xi 0, 0 plus Xi 1, 0. With the joint hidden states, we can rewrite the null hypothesis as a composite null considering 3 possible cases with color black in this table. And the null proportion would be the summation of these corresponding probabilities. Then we can have the maximum p-value. We need 2 assumptions. The first is that the non-significant p-values would follow a standard uniform distribution. And the second one is that p1 is independent of p2 conditionally on the hidden states. With these 2 assumptions, we can have the distribution maximum p under each hidden state of the composite null. For 0, 0 case, we can have the exact distribution. For 0, 1 and 1, 0 case, or one p-value is significant and the other is not, we can have an upper bound of maximum p distribution. Next, we can use a Bayesian formula and get the upper bound of max p distribution under the null. If we denote the upper bound as a function g of t, it is less than or equal to t, the CDF of standard uniform distribution. So we could say, under the null, the maximum p follows a super uniform distribution. That is why JUMP got its name. When we reject the null hypothesis with a maximum p-values bounded by the threshold t, we can have an upper bound of false discoveries. It is m times null proportion times gt, and the total number of discoveries would be the total number of the maximum p-values bounded by the threshold t. Then we can have a conservative estimation of FDR, which is a ratio of the 2 terms. Under the oracle case, where the joint hidden state probabilities are known, we can have the rejection threshold, which is a supernorm of t, where the FDR estimation is upper bounded by alpha. Then we can reject all the null hypotheses with a maximum p-values less than this threshold. This procedure can control the FDR. Our next step is to get the estimations of the joint hidden state probabilities. We first apply Story's approach to get the estimations of pair 01 and pair 02 as functions of tuning parameters. If you want to get the estimation of pair 01, it can be estimated by summation of p1 larger than some tuning parameter lambda 1 divided by m times 1 minus lambda 1. Pair 02 can be estimated in the same way. Then we extend this estimation to the 2-dimensional case and get the estimation of C00 probability that both theta 1 and theta 2 equal 0. Noting that these estimations are functions of tuning parameters, we use some smoothing method to choose these tuning parameters to make sure these estimations are good and consistent. Then, using the properties of the joint hidden state probabilities, we can get the estimations of C01 and C10. With these estimations, we can plug them in to get the estimation of FDR, which is totally obtained from the data we have. Then we can repeat the process as an oracle case, find the threshold and reject all the null hypotheses if the maximum p is bounded by this threshold. This procedure can control the FDR, but a little issue is that this threshold is a little hard to obtain because the FDR estimation is not a continuous or smoothing function. To release a burden of computation, we propose an equivalent step-up procedure. We first order the maximum p-values from smallest to the largest. Then we find the largest k, where the case ordered maximum p-value would make the FDR estimation upper bounded by alpha. With this k, we can reject all the null hypotheses corresponding to the first k ordered maximum p-value. Recall the 2 assumptions of standard uniform of non-significant p-values and conditionally independent of p1 and p2. When these 2 assumptions are met, we could say our procedure can control the FDR at level alpha. This is a whole picture of JUMP. Next, let's look at its performance in simulation and data analysis. In our simulation, we consider the one-sided z-test with a test statistics generated from normal distribution with different mean and standard deviations. The p-values are calculated by the right-tail probability of the standard normal distribution. We consider 10,000 of genes, fixed linear proportion 0.05, and check the other hidden state probabilities of the null. JUMP is compared with the following methods. We have talked about BH and maximum P before. I'll just first screen on the p-values and then use some BH-like method to the screened p-values. MAR tests the replicability by the ranks of p-values. IDR captures the dependence of P1 and P2 by constructing a bivariate normally distributed copula. This figure shows the FDR of all these methods with different signal strengths, standard deviations, and K0, and this horizontal dashed line would be the FDR nominal 0.05. We could say for all the scenarios, our procedure, the red one jump, could control the FDR very well. And the other methods, for the other methods, some methods could not control the FDR, like BH and IDR, and some others might be too conservative, like maximum P. Then let's look at the power. Or we could say jump has higher power than the other competing methods for all the scenarios except the first row. But we can go back to the FDR. In the first row, the brown one, BH, could not control the FDR. So it is meaningless to talk about its high power. When we discard BH in the first row, we are still confident that jump has higher power than the other methods which can control the FDR. Then we apply jump, BH, and maximum P to the mouse olfactory bulb data from two studies. One study is using ST technology, and the other is using 10x Visium technology. We will apply Spark method to obtain the p-values, and we have the input about 8,500 pairs of p-values from these two studies. This Venn diagram shows the total number of discoveries of these three methods. We could say jump could capture almost all the discoveries of maximum P and jump and BH. Besides, there are 170 genes that can be only discovered by jump. That shows that jump is more powerful. But one question is that, are these discoveries reliable? Then, for all the genes discovered by jump, we cluster them into 3 different layers and reconstruct the special expression pattern in the two studies, ST in the first row and 10x in the second row. We could say for all the 3 layers, the special expression pattern can be well maintained in the two studies. That shows the overall performance of jump is very good. Then, for the unique genes that can be only discovered by jump, we randomly choose 3 genes and reconstruct the special pattern. In the two studies, compared to the original one, the special patterns are well maintained. Does that show the unique genes are good? Some audience might not be convinced because it's just performance of 3 genes out of 170. Then let's look at the summary statistics. We choose a Moran's I statistic, which is a measure of the special autocorrelation. This figure shows a box plot of Moran's I statistics for the common genes that are discovered by all 3 methods and unique genes that can be only discovered by jump in the two studies. We could say in both of the two studies, there is a higher distribution of Moran's I statistic in the unique genes compared with the common genes. In conclusion, in the data analysis, our jump can find more discoveries. It is more powerful. Besides, the performance of all the genes and unique genes of jump is very good. In summary, our procedure can identify replicability from 2 studies by giving an approximation of false rejections. It is easy to complement. We don't need to get the estimation of alternative density functions or P, and we don't need to assume the two studies have the same spatial alignment. However, for now, it can be only applied to the 2-study case. When we have n studies, the total number of the parameters to be estimated would be 2 to the n-1, which would explode if n is getting large. We will leave it for future research. These are my references. I would acknowledge the work of my co-authors. Thank you for listening. I'm glad to answer any questions.
Hi, thank you, Pengfei, for the great presentation. Are questions from the audience? Or you can have any questions from the for the previous speakers. Okay, if no, I would like to express my sincere thanks to all of the speakers today. Thank you all for the great presentations. I think you all did a great job. Yeah, maybe we could move on to the next section. Yeah, and then we'll have a break until 1:30, and then we'll have a keynote speech from Xihong Lin from Harvard University. Yeah, thank you all.